share screen. Share my presentations in PowerPoint platform. And after that, we are gonna do our courses like in a conventional method. We are gonna write the screen while I'm explaining the problems and the concepts. I'm gonna write on the screen. You're gonna take notes. Okay. In the first 3 weeks, these are the fundamental part of the statics. That's why I'm gonna show you some photos from some sketches. That's why I'm gonna use this method here. Okay, first 3 weeks. After that, you have to take notes. Actually, what I suggest you, okay, there is a presentation here. At the end, I'm gonna share with you. Okay, I'm gonna put this to Moodle platform. It's a new platform for me. I'm sorry, I tried to learn how to put or upload something to there, but I will learn it soon. So I will upload this to the Moodle, but I suggest you take your own notes. Okay. At the end of the day, it's a presentation. If you look at only this presentation, you can find millions of presentations in Google. So you can look at the presentations and you can solve every problem. No, it's not easy like that. So please take your own notes while I'm explaining the concepts here. Okay, you're gonna get the presentation. It helps you, it supports your notes. This is my suggestion. If you follow this, you're gonna be more relaxed in the next stage. Otherwise, you're gonna be stressful. Oh, what I'm gonna do? We never ask anything. If we don't do that in class. Okay, let's get started. By the way, here today we are going to talk about structures, loads, and the force concepts. What is the force? What are the components of a force? Let's get started. Here we are going to talk about the here there's a word, a body. Okay. Study of what happens to a thing when forces are applied to it. Okay, what the mechanics is, it's a kind of study of what happens when we apply a load to this structural member. For example, we technically, all these structural, we are gonna name all these members as a body. Okay, this is a technical word to explain member. This is a body. Here, this is a wheel of a train. That's okay. This is a kind of body for me. And here there is a trackway. This is a body. One body on top of the other one here. And it gives us here a point load, as you can see, or as you can imagine. And this trackway gives up a reaction. So this is a study about this behavior. Okay, this is an example. You can change these examples. For example, here there is a metal member here. There's a metal body, and we hold this metal member with a chain system. So we apply a load to carry this body. So this load divides to like this, like this. So it's in a balanced position. The mechanics works on this behavior, on this balanced situation. If we apply a load, what changes? How we can calculate the forces in the members? How this force affects the other one? Okay, this is the mechanics. This is the mechanics is a general title at the beginning. Now you're gonna see the breakdown of the mechanics. You can see here mechanics of the rigid bodies, deformable bodies, and mechanics of fluids. Okay. The last one, you're not gonna deal about this one. Okay. This is fluid mechanics. All the engineers are deal with this, especially the structural engineers or hydraulic engineers who designed the dam, because or who designed the marine structures. Okay. It's about the fluid mechanics, wave mechanics, etc. It's or mechanical engineers works about this. If they design an engine, the oil, or I don't know, the fuel transfer is a kind of fluid mechanics problem in the engine. So this is an engineering case. Okay, we are not gonna work on this part. Okay, what we have at the moment, rigid body and deformable body. I'm gonna explain what the rigid body or deformable body. You know what the body is. Body is a member. Okay. It can be a structural member. It can be a in our problem, it can be a wheel of train, as I showed you in the previous page. We call these type of members as a body. Yes, but we have here two different types of bodies, rigid and deformable. In the next page, I'm going to show you what the differences are between the rigid and the deformable bodies. Under rigid bodies, statics and dynamics we have. And under the deformable bodies, we have mechanics of materials. So what is the name of this course? Is statics. We are in this page. Okay. I'm going to show you what is the differences between these two, statics and dynamics. You don't have to memorize this. I'm not going to ask this part, but you have to imagine what we are doing. Okay, let's talk about the rigid body first. Rigid body. Here, you can see three examples in the middle line. Okay, the first one is a box or a stone, a cubic stone. Okay, let's say. Or forget about the material type. Okay, we have a cube. That's better. The first one is unloaded position. If there is no load on this member, there is no deformation. It stays there as its initial position. So let's have a look at the second one. I have a rigid body. Look here, the name. Okay, I have a rigid cube. Rigid cube. That means if I apply a load to this member, it doesn't make any deformation. Okay, it doesn't make any deformation. It stays on its initial position. Okay, the example is stone here. If you have a huge stone, you can apply a load, it doesn't change its shape. Okay, at the end, if you apply a huge load on top of the stone. Okay, it crashes. That's okay. But I'm not talking about this crash mechanism. I'm just talking about I have a body here. If I apply a load on top of this, it's not gonna do any deformation. Let's have a look the last one, deformable body. The name comes from the behavior, deformable. When we apply a load on top of the member, I'm sorry, it makes deformation. Okay, it makes deformation. So the example for this one is foam. You know, it's a soft material. When you apply load, you can see the deformation. It's deformable body. But here in this course, we are going to talk about rigid bodies. Okay, rigid bodies. Keep this in your mind. If there is a rigid body, it means no deformation. Okay. Is this part okay? What the rigid body is? Is this okay?
Yes, teacher.
Okay. I'd like to hear from you actually. We know now what the rigid body is because I'd like to explain these small or fundamental definitions at the beginning, because in the next stage we are going to see in examples we are going to see a rigid body word or rigid member word. So I will accept that you know what it is. Let's go ahead. Okay, this is the more detailed of the mechanics of rigid body. Okay, we know that if we have a rigid body, we have no deformation. That's okay. In the first line, if we break it down, we are going to see the statics and dynamics part. You can see the static part is dark and the dynamics part is light here because we are at the left side. But I will explain again what the dynamics is. Okay, dynamics has two breakdowns, kinematics and kinetics. But at the left-hand side, what we are gonna do, statics has forces and moments. Today, we are gonna talk about the force, what it is, what are the components are. So in the next stage, next week, we are gonna talk about the moments. I guess most of you familiar to moments and forces if you come this architectural division from science division from high school. I think you are familiar all these terms, but in this stage we are gonna make some different applications. The method is same, but we are gonna do some different applications. Here, if we have force, it's about linear equilibrium, linear balanced situation. If we have moment, angular equilibrium. Angular means in while we are gonna explain moments, we are gonna see the moment is a kind of rotation. So it makes an angle on the structural members. So we have rigid body, one step down, we have statics, one step down, we have two branches, forces, moments. That's okay. This is a general definition. Okay, here we are going to compare dynamics and statics. Okay, statics. Okay, we are going to deal with bodies at rest. Rest means, okay, here, this is surface. I have a box on this surface. It stays here. There is no movement in any direction. This means this body is in rest. Okay. or statics deal with bodies move with constant velocity. For example, if this moves to this side with, I don't know, 10 km/h, its velocity doesn't change. It always goes in same velocity. Okay. If there's an acceleration in the velocity, it's not the subject of the statics. It have to be in the dynamics. I'm gonna show you in the next stage here. Because when we look dynamics, it says, okay, we deal with bodies accelerate or decelerate. Or here, dynamics deal with the member interaction. For example, momentum change. You can remember this question. The ball comes in this direction. Here we have another ball, and if it hits this one, it transfers the momentum to other one. The other one starts to move. That's okay. This is the momentum change. This interaction is the subject of dynamics. In this course, we are gonna deal with these two steps. I guess you understand the differences between the statics. In statics, we are in rest position or we have a constant velocity. But in dynamics, we have acceleration or deceleration and the interaction of the bodies. One hits the other one. Like this is an example. Okay. These are the examples for statics and dynamics. Okay. Now we understand what we are gonna do. What is statics? What is rigid body? But here, I'd like to explain what is a structure. You can find these definitions in books. You can find the better definitions than this in Google. That's okay. Let's have a look at the book definition first. Structure is defined as something made up of independent parts in a definite pattern of organization. Okay, what is this? We have independent parts to make a structure. This is the philosophy behind the structure. We have independent parts. What we would like to do, we want to put them together in a pattern. We don't know what it is. The pattern is a general definition here. We'd like to put them in a pattern in an organization. So at the end, we would like to get structure. We would like to carry something. This is our aim. In the natural world, what we would like to do, we would like to do the most powerful building. We would like to get most strength with using least material. We would like to the most strengthful structure, but we would like to use the least material. Okay, so this is the general idea. We can do large structural members in our buildings to resist any natural disaster. That's okay. It's not economical. We have to use least material. Okay. This is our aim in design. And this should be your aim, actually. You can see here at the right-hand side, there is a spider web. It's a good structure. I like to give this example as a structure, this example. You know, there's there are, independent parts. You can see all these members are independent. Okay. But if we put them all together, we have a pattern in an organization, you can see. And this is really a powerful structure. It has really big strength. And at the bottom, you can see Eiffel Tower. It's a general example. They used, again, independent steel members. And the designer, the engineer, put them in an organization, put them, here, the organization is a project, in a design for a building. They put them together according to a good design. And at the end, they use least material and get a really well-known structure. Okay, this is the general idea behind the structure. What we get, most strength. What we give, least material. Okay, this is our aim. Did you get the point here? Hey, are you there, guys?
Yes.
Yes.
Okay. Okay. Sounds good. Let's go ahead. Stability and strength. You're gonna hear about all these two words in this course, in the next stage, in the strength of materials course, in the next term, and also in your professional life. If you deal a project and if you work with an engineer, you have to understand what engineer says, because they're gonna say always something about stability and strength. You should know what the stability and the strength is. Here, let's have a look to stability. By the way, first I'd like to explain the strength. That's the easiest part, strength. Okay, please look to sketch here. There is a guy over there and trying to carry a weight on top of his head. Okay. So I'm a powerful guy. I'm gonna carry 100 kilogram and put it like this. Okay. If I have a power to do this, that means I have strength to carry this load. Okay. This is the strength. The size and the physical makeup of the structural materials are made sufficient to withstand the various forces acting on them. Here, if I have this weight here, I withstand this force. I carry this load here. If you think about your structure, for example, a building, you have to have a sufficient strength to withstand the earthquake effects, live loads in the building, wind effects, snow loads. We have many natural loads and also occupancy loads. If we have sufficient strength, we can carry all these loads and we stand. Okay. This is the strength. But what is the stability? Stability. Before I show you the sketch, okay, I'm here. I'm here with the weight on top of me in the balanced position. I carry all the load. If I lost my balance, I can go left hand or right hand side. I can fall down. This is the stability problem. Okay. If we are talking about stability, we have to provide, we have to be in balanced position. We have to be in balanced position. We have to prevent any sliding, bending, or twisting. For example, sometimes there are, sometimes you can feel like this. If you carry a heavy load like this, you can lose your balance and you can twist like this. It's possible. This is the stability lost. If you keep the balanced position under all these loadings and under all these effects, that means you have stability. Sometimes, for different cases, our structures lost their stability. So we have to make a design, or we have to make a stable design. Okay, there are some checks. There's a method. It's about calculations. You're going to use calculators in the next stage. But here, I'd like to give you an idea, an approach to understand, okay, what we are doing, why we are going to do all these calculations. Okay, calculation is calculation. At the end of the day, it's man-made. But if you understand the problem, you make designs, you amend your designs to solve the problems. Sometimes what I saw in my professional life, I get an architectural design. When we look the architectural side, it's perfect. But in terms of structural engineering, there are some stability problems. Okay, what we want, we don't want to change all your design. No, I don't like to make an engineering like this. But what I want from you, to make some amendments, to make some small solutions to solve these structural unbalanced behaviors. Okay, let's have a look at this one. Here you can see the stability. You can see the stability. If you lost your stability, you can fall down like this. For example, if you lost your strength, okay, the weight is on top of your head, lost your strength suddenly, you start to go down a little bit like this, under this heavy load. These are the stability and strength problems. I like the sentence at the bottom. Without stability, the strongest of buildings will fail. And again, without strength, the most stable of buildings will fail. So what we understand here, if we have one of these stability or strength cases, we don't have anything. It's rubbish. It's gonna fail at the end of the day. So in our designs, we have to provide both of these cases. We have to provide stability. That means we have to provide a balanced condition for the loading condition of our structure. Because if you design a chair, your loading condition is a man sitting on the chair. If you design a dam, you have a huge water pressure behind that. It's a kind of loading for. If you design a building, you have many types of building, many types of loads, natural loads, wind, earthquake, snow, and also live loads, the occupancy loads, or that load. That means the self weight of the structure. All these are the loads. Under this loading conditions, we have to provide stability and strength. Okay. What time is it, by the way? By the way, I'm gonna give a break at 11:15, half an hour. Okay, half an hour. Then we are gonna start the second session. We have 15 minutes. Are you okay at the moment? Seda, are you okay?
Okay, teacher.
Okay, Didem Aydın. Okay, good. Okay, loads. I would like to explain the loads. Actually, this is the only session we are gonna talk about the loads. In your design, you know, you have many design courses or architectural history courses, whatever. In these courses, we don't talk about the loads. We have to know about the loads because, you know, we are in a war or we are in a fight with these loads. We have to beat all of them if we want to have a good design. Okay, gravity loads. Gravity means gravitational loads. The vertical loads. Okay, gravity loads in the gravity direction. Okay, dead load and the live load. Let me see. Okay, I'm gonna show you some examples. Dead load and live load. Dead load in Turkish zati yükler. Okay. Or ölü yük. It's same in Turkish. Sorry for the Turkish words, but if you have a chance to take a look at the Turkish books, you are gonna see these words. Live load is not in Turkish canlı yük. It's not canlı yük. It's hareketli yük. Okay, please take your notes. Live load is hareketli yük. I'm gonna show you the differences between these load cases in the next stage with this sketch. Okay, let's jump the other box, lateral effects, lateral loads. You can see here the main. By the way, I'd like to add other loads to gravity loads. For example, snow loads. Please take a note here. Snow loads. It's a natural load. There are many examples. If you have a building, an industrial building, there is a crane inside to carry heavy pieces in the building. So, for example, this is 100 tons capacity crane. That means this 100-ton load goes to these columns. So we have these type of loads. In the next box, we have lateral effects and loads. Why I say effects or loads? In the next stage, I'm going to explain. We have seismic and wind. Seismic and wind load, wind effects. And let's jump the next box, dynamic loads. For example, a moving car or crane. This is a kind of crane is a different case, but you can accept this as a dynamic load. Yes, this is a kind of dynamic load. Yes, it should be in this case. A moving car on a bridge. We have a bridge structure. On the bridge, we have a car which moves. So it's a kind of dynamic load. Or we have a high-rise building. So we have really fast and cutting-edge elevators in these buildings. This is a kind of moving load for my structure. Okay. These are the examples. Impact loads in the next box. Explosions. Let's say you have a tank or you have a chemical material stock area. If these materials or the gas in tank explode, we are gonna get explosion and explosion loads. We have car crash. We encounter these load types, especially in the columns of the bridge. You know, there is a bridge here and there is a way under the bridge, and suddenly the car hits by accident to one of these columns. It's an impact load from our structure, or bomb blast, or a terrorist attack. It's a kind of impact load because these loads occurs in a short while. So it's not it's not like a load. For example, I'm a load in this building. It's not like my walk on the slab. It's a sudden impact load. It hits the building suddenly, so it gives more damage. So it has a different design method. Okay, but well, here in the big picture, what we learned here, we understand the load types. Okay, let's go in detail. Here, dead and live loads. Okay, let's have a look the left-hand side. There is a flat, on the flat, you can see the wall structures and the slab beams, which are the main members of the structure. But inside, there is a man, some furniture, bookshelf, whatever. Here, what I'm trying to explain you, what is the differences between live and the dead load? When you look at the table or chair in this building, is it live or dead load, and why? What do you think? I'd like.
Yes.
Why?
Because they can move, but bookshelves can't move. And we make it like stay in the wall.
You mean the furniture? This, for example, you mean this member, and this one is live load.
Yeah.
This is a fixed member on the wall. This is dead, right?
Yeah.
Okay. Now, there is a main differences here. All these are live loads. Okay. This is not a dead load. What is the dead load? The self weight of the structure. You can see I have this building, the self weight of this beams, slab, I don't know, concrete wall, whatever, all the structural members, this is dead load. And also, if we have an architectural floor finish here, this is dead load. These are the dead loads. But inside the building, when we start to use this building, we can put bookshelf, we people, pedestrians, or furnitures. All these members are live loads because you can move them. You can put the bookshelf here, and then after 2 weeks, you can put it here. It's possible. It's live load. Dead load is the self-weight structure and floor finishes. These are the dead loads. All other stuff are live loads. Here, let's have a look at the second sketch. Please look at the bottom one. There is a room. There is a guy sitting next to computer. There's a table and carpet on the ground. Here, only the walls, these parts, all these structural members and these walls are dead loads, and all other things are live load. Even this carpet, this is also a live load. These guys, all these furnitures, these are live. Okay. Let's have a look to roof. Here, there is a roof structure. You can see the setup. You can see the different layers. Over here, there's a structure, and there are some wood tiles on the frame members, and on top of this, roof tiles, you can see. So all these are dead loads. What is the live load? The snow is live load. If a worker climbs on top of this roof, and for example, for a maintenance work, it's live load. Okay, and all other stuff here is dead load. Okay, question. Did you get the differences between dead load and live load?
Yes, teacher.
Okay, sounds good. Oop. Jump to next page. Wind loads. Okay, wind. Wind is a kind of air transfer from the high pressure area to the low pressure area. Okay, because you know the pressure zones on the atmosphere, it's a transfer of this air from the high pressure zone to low pressure zone. So this makes the wind. So when the wind hits our structure, it makes some pressure on our structure. It might make some suction or uplift, as you can see in the first sketch. Or for the high-rise buildings, the wind shakes the buildings like a pendulum. Actually, you can have really a powerful strength for wind. Okay, your structure sometimes doesn't fail, but if you don't provide stability for high-rise buildings, what you are gonna see when you are walking in the top floors, you are gonna feel a shaking, and it's not a comfortable situation. So you are gonna get sick depending on this shaking behavior. There are many examples in the world. The buildings are shaking. So they are trying to solve the problems after construction with the cutting edge technologies to reduce this shaking under wind effects. So wind depends on wind effects, wind loads, depends on building height, building shape and geometry. The relation with the adjacent buildings, location and terrain. So if you have a building in Beşiktaş, for example, and if you have a building in Istanbul, Beşiktaş, and close to the sea level, for example, in I don't know, in Kayseri, for example, maybe we have a friend from Kayseri. One of the Kayseri's hills, we have a building. So the wind nature and the force is different. If you are close to seaside, you are gonna get less wind load. If you are on top of a hill, you are gonna get higher wind effects, wind loads. So that's why this depends on location and terrain. Okay, let's go ahead. Seismic effect. Okay, this case is a little bit interesting. I don't like to use the seismic load. Actually, it's not a load. Actually, there is no load. There is no a real load on the building. If we think about the wind comes to my structure and hits it. So it makes a pressure on the building. So it's a kind of load because there is a pressure on the building. But here on the seismic case, there is no load. Have you ever seen any load like seismic load? No, because there is no physical load. For example, I have this glass. If I push this glass, okay, I have a structure. There is a physical load because I pushed this glass. In the seismic event, think about the seismic event, how it occurs. Basically, we have an epicenter where the earthquake starts. Okay, where this is generally on a fault line. Okay, fault, fay hattı. Okay, if this fault slides, earthquake starts. The start point of the earthquake is epicenter. Okay, epicenter. That's okay. And when this movement starts, a ground shaking. Actually, this action, this movement, release an energy to the ground, and this energy is transferred in the ground by shaking, like this. And it comes to my structure. By the way, if you try to understand this fault slip or start of the start point of the earthquake, please do this. Look at me, please. Please look at me here. Okay, you can try this yourself. Okay, we are gonna do this. Okay, now give pressure both of your fingers. Okay, give pressure and try to do this. Try to do this. When you give more pressure, you are gonna get higher sound. If you don't give any pressure, you can't get higher sound, a low sound. This is nothing. So this is about the slip of the fault. There is a two ground portions, and they apply a force to each other. Somehow, at some point, they slip, and the sound, which is the energy, releases in the ground. Okay, we understand how the earthquake starts. Now, okay, we said there is a ground shaking, there is a wave in the ground, and it comes to my structure. From here, where am I? I'm in the ground at the moment here. Did you see anything before? From this point, it jumps to top of the building and push the building in one side. Did you see anything like this?
No.
Of course. Yes, you're right. We are now here. What the earthquake makes to my structure. When you look at, it's really difficult to explain this this phenomena to engineering students as well, because what they see in their books, always they draw a building like this. Okay, this is my building, and they see a earthquake load distribution like. So the earthquake is only a load for them. But here, I always try to explain it's not a load. It's not a triangular load like this. It's an effect, how it works. Okay, we are here. The earthquake, for example, here, suddenly takes this point, right hand side. Sağa doğru çeker. Takes this point to right hand side, for example. Or in this example, how it works? Sorry. In this example, the second one is here. It takes the ground to the left hand side. Suddenly, the time is less than a second. It's like a millisecond. It's so fast. So look here, the first sketch. This is the initial position. When I move the bottom part, so when I move the ground to left, the bottom part goes to left. But top part is at the initial position, almost initial position. That means this comes from the Newton's rule. If a body stays in rest position, it always wants to be in the rest position. Eğer bir eleman duruyorsa, hep sükut halindeyse, hep o halde kalmaya çalışır. Onu ister daha doğrusu. Okay, here we move the ground to the left hand side. So depending on this movement, the bottom side goes left. So top side is at initial position. But this behavior is so fast. Okay, I'm explaining this in 10 minutes. It takes less than 1 minute. So imagine the velocity of these waves. Okay, here. And suddenly, in the second shake, the ground goes right-hand side. It goes here. This top point goes left. And the shake, after this first action, the shaking starts. So this wave, this energy only gives an acceleration to my structure. So basically, you know this equation. This is a really basic equation. Okay. I don't want to explain more detail about these calculations, but it comes to Newton mechanics. You know, this is the mass. Mass. This is the acceleration. So this action starts, this shaking starts. During this shaking, the ground gives my structure an acceleration. So if this acceleration makes some inertia forces in my structure, mass times A acceleration, which is the force. This gives, or this makes an internal force in my structure. There is no load at the perimeter of the structure. Okay. This seismic load occurs due to the acceleration on the ground. So and this effect, the seismic effect, depends on the mass of the structure. If you have a higher mass, you're gonna get higher earthquake effect. If you have a low mass, you're gonna get lower seismic effect. So sometimes we fight with the seismic effects with using the mass. We sometimes change the mass of the structures. So you get the point. That's why the seismic is not a load, it's a kind of effect. Let me see. It's 11:20. I missed the hour. Let's have a break, half an hour. Half an hour. What? We are gonna be here 11:50. Okay. Okay.
Okay,
See you.
teacher.
Okay. See you guys.
See you.
Yes. Share screen. Oop. Oop. Can you see my screen now?
Yes.
Okay. I think I gave this seismic hazard map of Turkey for you. I guess I hope it gives you an idea about the seismicity of the regions or cities in Turkey. Here you can see this map in the website of the AFAD, and you can see here the red or dark red lines. These regions mainly the fault line zones. This part is the famous fault line, which is the North Anatolian fault line, and there is one more big line here. They intersect to each other around this region. You can see the seismicity in these regions are really high. And if we have a look to Aegean side, the west side of Turkey, you can see this part is reddish. And okay, that's okay. There are some dark red regions, which are the fault lines. And here around here, there are different faults in the ground and in the seasides. Actually, you may remember the last year's Izmir earthquake. The earthquake was in the sea. It occurred in the sea next to the one of the islands here over here. So why I'm showing this map? If you design a building, maybe you like to see the or remember the seismicity of the that region. You can just take a look at this map. Okay. The interesting equation we have here, the risk, seismic risk. What is it? It has two components, hazard and vulnerability. Hazard and vulnerability. What is the hazard? Hazard is made of nature, actually. It's a natural thing. We can't change the hazard, okay, in this risk equation. If we have the North Anatolian fault here, we have that. We can't change its location. So what we can do to change the seismic risk, we can deal with the vulnerability. It's about our design, our building quality, our structural quality, or our material quality. So regarding the vulnerability, as you can see, there is a photo from the 1999 earthquake, Marmara earthquake. So if we do good design, seismic proof buildings, we can reduce the risk. We cannot change the hazard. What the Japanese people do, they have a really, really high seismic hazard, but they work to reduce the seismic risk. They deal with only this part. They find cutting edge technologies to reduce the seismic effects on the buildings. They make more stable and strengthful buildings. So more ductile buildings also. So in this equation, what you have to know, we can change something with the vulnerability part. This is what we can do. The other part is out of our control, the hazard part. So as a designer in your designs, you can reduce the seismic risk. Okay, here I want to point out this point. You can do that. You cannot deal with the natural things, but you can do, if you do better what you do, you reduce the seismic risk. Okay, here, dynamic loads. Dynamic loads are sudden applied loads. Loads change rapidly or result of amplified rhythmic movement. Elevator loads, car in a garage structure, or a car on a bridge, or a soldier group working as a team with a rhythmic movement. All these things gives our structures dynamic loads. Okay, dynamic loads. Okay. What we did so far, we discussed what is the structure, what are the bodies, rigid body, deformable body. We discussed the stability and strand. What are the differences? And then we try to understand load types. We have different load types, and we try to explain what are they. By the way, in the chat box, there was a question, Chad. I think you asked that question, doors and windows. You know, you have a door frame or window frame. You ask, are these dead loads or live loads? I guess you can change the window frame, door frame in the next stage whenever you want. So if we think that in this manner, yes, it's live load. It's live load. Okay. Now, from now on, what are we gonna do? We are gonna talk about the force. What is the force? What are the components of the force? How we can resolve the forces? As you can see here in the picture below, there is a pole, and on top of this pole there are 3 cables. All the tables are in tension. So basically, if we look them on the pole and the cables, it's nothing for us. But if we look the problem from the static side, in a technical perspective, we have to see forces over there. If there is a tension, there are 3 cables, there are 3 different forces which act on top of the pole. Okay, this is an example. Let's go ahead. Okay, components of force. Here we have a line of action. Okay, line of action. Just a second. Here we can say LOA instead of line of action. So in the next stage, application point. Okay, we apply our load to this point. It's important where my load acts on. Okay, we have a load, that's okay. But where is the application point? It's important. If we change the application point, the effects of the structure change on the buildings, on the structures. That's why the application point is important. So I have an application point. I have a line of action. Line of action means my force is gonna be on this line. It can go this side, this side. Okay. Oh, sorry. This is the application point. Okay. Do we know what we need next? We have to know the direction. Okay. Because this load gives a different effect. This load gives a different effect to my structure. So the next stage, yes, I need a direction. What I have, line of action, LOA. On this LOA, I have an application point. That's okay. Okay, I know my force is going to be on this LOA, but the direction is important. That's why we have to define the direction to emphasize a force, to show a force. Okay, there is one more thing missing. What's that? What do you think? Do you have an idea? Oops. There's a problem here. Okay, the next one is magnitude. Magnitude. So I have application point, I have direction, everything, but the magnitude is important. Is magnitude 10 tons or 1,000 tons? There's huge differences. So we have to know the magnitude to define a force. Okay, so just a second. What we have as the components of force, line of action, application point, direction, and magnitude of the force. Okay, we have to provide all these four things to define a force. Okay, that's the thing we have to watch out for. Principles of statics. Okay, what should we do? Force is a vector. That means we cannot do any scalar calculation. So all our calculations have to be vectoral calculations. Okay, this is the most important point of our calculation. We don't make scalar calculation. Okay. Okay, vector operations. To remember, let's remember the vectorial operations. I guess you can remember your high school knowledge, but I would like to remind that again. For example, we have a force, as you can see here, which is A. Okay, its direction here. If we have negative a or minus a means on the change on the direction, okay, because all these are vectorial calculations, okay. If we have a negative sign, that means we have to change the direction to the opposite side, okay. Okay, here we have a vector which is a. If we like to calculate the 2 times a, if we multiply this vector with a scalar number, what we have? Its magnitude gets double. Okay. Its magnitude. Direction is same, as you can see. Application point same. LOA same. Everything is same, but the magnitude doubles. So another example here. I have minus 1.5a. Minus 1.5a. If I divide this vector to a scalar number 3, for example, what I'm gonna get here, I'm gonna divide this number to 3. It's gonna be minus 0.5. There is no change on the direction here. And by the way, this is, if we think about a is here, minus I have, the direction is changed, and then 1.5a, the magnitude is 1.5, and it's same for the minus 0.5a. Direction is changed due to this minus, and magnitude is half of the a at the initial position here. This is the scalar multiplication and division. Vectorial addition. Vectorial addition. What we do, if we like to sum this a and b vectors, we don't do, for example, this is 2, this is 3, we don't do 5. This is a scalar calculation. Here we have to consider the direction, magnitude to calculate the summation. What we do, we connect their start points to each other with the directions, as you can see, and complete it to a parallel. And if we connect the start point to the end point, we are gonna get a resultant force, which is the summation of these two A and B forces. To define this R, okay, the R gives us only the magnitude. To define this, we have to give also the angle. Okay, angle. Any questions so far? Okay. Here, what we have, A plus B with the triangle method. If in the parallelogram method, what we did, we connected to start points to each other. Here in the triangle method, what are we gonna do? Okay, this is the first vector, start point, end point, arrow point. And the first end point connects the second start point. As you can see here, there is an arrow. and also this is the start point. So we can connect them to each other. Why the directions are important? So, okay, we can, with this method, we can calculate this R. We can calculate them magnitude, but at the same time, we have to define, we have to show the direction of this R. That is also important. That is also important. That's why we always consider all the directions given in the question. We have to consider all of them. If we have subtraction, what we do? This is an addition, this is subtraction. So that means there is a negative vector here. Here you can see A, and B minus B. What was the minus means for the vectorial calculations? You can remember from the first page. If we have a negative vector, that means we only change its direction to the opposite side. So after I change the direction, opposite side, I have minus B. Minus B, that's okay. Minus B is this. Okay, so I can use one of these methods, parallelogram or triangle method, to calculate the resultant force. Negative means always opposite side. Okay. Okay, force shift method. Force shift method. As you can see here, the gray member is a rigid body. Rigid body, what was it? You can remember. Rigid body means no deformation under any loading condition. Okay, rigid body. So I have a load here which acts on this point. I have a rigid body. So you can see LOA, which is the dotted line here. Okay. If I change the location of the force, this force, on the LOA from, I can shift this force from this point to here. As you can see, this is the initial position. This is the last position. So what was the rule? It have to be on the same LOL. Okay. We are on the same LOL. We only shift the force. We don't change the location of the force. Okay. We shift the force on this LOA. So at the end, what we get, no change on the balance. The balance situation doesn't change if I do this. Why I'm explaining this? Okay, there is no change, that's okay. But in the next stage, to solve the more complex problems, sometimes we have to change the location of the force. So we are gonna use this method, force shift method. If I change its location in the same LOA, there will be no change on the balance of the body. Okay. This is the force shift method. Okay, we have a rigid body again. You can see the LOA, which is the dotted line. On this LOA, I have two different forces. One is here, as you can see at the left side. The second is at the right-hand side, as you can see here. If the rigid body is in the equilibrium condition under these two loads, that means these two loads have same magnitude, M1 M2. Their magnitudes are equals to each other, but they have opposite directions. Okay, if a rigid body is in balanced condition under two loads, which are on the same LOA, that means the magnitudes of these two forces equal to each other, of course, but they have the opposite directions. Okay, this is the equilibrium rule. Okay, superposition. Balance doesn't change when balanced force couple is applied to a balanced rigid body. Let's say we have a rigid body, and on this rigid body we have the black forces. So under this loading, the force condition, this rigid body is in balance. That's okay. If we apply a balanced load system on this existing balanced rigid body, that means the latest situation, as you can see on the screen, latest situation is when we apply the red forces, which are in equilibrium, to the rigid body. The system or rigid body stays in the balanced position. The balance doesn't change. If we have a balanced rigid body, and if we apply a balanced force system on this rigid body, the rigid body stays in the balanced position, balanced condition. Okay, this is the superposition rule. Okay, action and reaction principle. Basically, if you push the wall with 20 kilogram force, it gives you back again 20 kilogram force. That means if you punch the wall 100 kilogram force, you break your fingers. Why? Because there's a reaction on the wall which gives you back that 100 kilograms. So this is the action and reaction principle. Okay. Etki tepki kanunu. Action and reaction principle. Force systems. Okay. And how we resolve forces into the rectangular components. This is the most important rule. I guess most of you familiar to this one. We are gonna use almost in all calculations in this course and in the next term, this method. So this method resolve the forces to rectangular components. For example, we have F. Look at the sketch, please. We have force F. That's okay. We have a start point, which is the origin of our axis, X and Y. So this force has an angle with X and Y. Here we know the angle between F and X. So if we know that, that means we know the angle between F and Y. So we know angle. So what we are looking for? We are looking for the components of this f in the x-axis and the y-axis, which are fx and fy. How we can calculate this? Remember the parallelogram method. If we sum fx and fy, we are gonna get the resultant force, which is F. But here we are doing the inverse of this calculation. We have the resultant force. We are just looking for the components of this force on the X and Y. So what can we do? Basically, we have F. We are going to use trigonometry here and triangles given on the sketch. If we have F and angle, you can see here the equations. Fx is F times cosine theta. F times cosine theta. So Fy is F times sine theta. This comes from completely trigonometry. If I don't ask this question as a force, if I ask this question, if I ask you a geometric question, for example, I have a, perpendicular triangle, I have theta, and I know the length of this member, which is F. What is the X and what is Y? The question is same here. This X is F times cosine theta, Y is F times sine theta. It's same like this geometry problem. So we are using here the triangles and trigonometry to solve this problem. So here, let's combine this fx and fy. Fx and fy. These parts are the fundamentals of the force. In the next stage, we have to use these rules in our calculations. So that's why please do more practice about resolving a force to the vertical components and or combining forces to get a resultant force. Please practice this. Here, let's do the opposite of this. We have fx and fy. Let's combine this fx and fy to get the resultant force, which is F here. What we do, we are going to use triangular method here. The Fx in the lateral position starts and end is the arrow end, and connect the second forces start point to this arrow point, which is here. We have this one first, and then connect the second one to this. What we have? Yes, this one. Then connect this point to this end. Okay. Now we have triangle. So if we know this magnitude, can we calculate this F? Yes. We are gonna sum the square of these two components and get the square root of the total summation. So like the hypotenuse calculation in perpendicular triangles, it's same. The important thing is theta. Why the theta is important? That gives us the LOA, the line of action, actually. It shows us the line of action. It defines us. That's why the theta is important. Remember, we have 4 components: LOA, line of action, application point, magnitude, direction, and magnitude. We have 4 components to define a force. So if we are defining a force, we have to define its angle. How we can calculate the angle? It's easy. It's easy. We can calculate the tangent of this angle. We have a triangle, as you can see. Basically, we are going to use the same method always. We have a triangle. You can see the tangent of the theta, fy over fx, right? So the arctangent of this value gives us the theta. So by the way, I forgot to remind you that you need to have a scientific calculator. Okay, not a expensive one, basically, but you need one. Otherwise, you can do all these calculations, because we are not. We will use some numbers with after the point. For example, we are gonna use some scientific number. We are not gonna use the p, for example, like 3 in our calculations. In your calculators, there is a p button. You're gonna push that button in the next stage when we use it. Or you can calculate this arctangent. This tangent power -1 means arctangent. You can do it by your calculators easily. That's why please get a calculator and please learn how to use it, because generally this is my experience from the past years. When the students come to the exam, they don't know how to use their calculator, because the first time they see it, before they came to the exam hall, they bought a calculator and they come directly to the exam. At that time, they can't do anything. You cannot calculate the arctangent. You cannot calculate the, I don't know, any other scientific operations. So to do this, please get a scientific calculator and learn how to use it. It's really important. Otherwise, you can't solve these problems. Okay. The problems are basic, but you cannot calculate the, for example, tangent, because our angles will be, for example, like this. You cannot calculate the tangent or arctangent of this number. It's not easy. This is not a special triangle's angle. Okay, I guess you get the point. You're gonna get your calculators. Let's go ahead. Okay, here we have an example. We have a connection which is connected to the ground. On this connection, we have 1000 kilonewton, kilogram, whatever. We are not dealing with the unit at the moment. 1000, and you can see the angle of this force, which defines the LOA of this force. The question is here: determine the horizontal and vertical components of the force. What we have a force, and this question looks for the fx and fy, the components on the x-axis and the y-axis. It's easy. we are going to use the same methods. Fx and fy. We are going to draw this one. We are going to draw two components, and we have the angle, which is 30. So what is this? The fx. If this is the angle, fx equals 1000 times cosine 30. What is fy? You have to know this from the trigonometry. This vertical line is the sine component of the force. So we are gonna write Fy equals 1000 times sine 30. You can see here the calculations at the left-hand side. Can you see the cosine and the sine components easily when you have a look at the force? Is it easy for you?
Yes.
If you have trouble, okay, you may have trouble, no problem. You have to consider the trigonometry. Okay, you have to take a look the trigonometry part, how we consider the sine and cosine components of the lengths. So this is easy. I guess you can do it easily because in the next stage, we are going to use this method in the complex problems. Okay, and the complex problems. But at the end, we are going to do the same thing. The problem may be a little bit more complex than this. That's okay. But the method is same. If you understand what we are doing, you can apply the same method to more complicated problems. So you can solve it. That's okay. I guess you can do that. Here you can see there is an I-bar. I-bar is a kind of screw. Sorry. It's a kind of screw. At the end of the screw, there is a circle, a closed circle, as you can see. So on this circle, there is a force, as you can see. The magnitude is 150. I'm not giving here again a unit. That's okay. There is a unit, kilonewton, ton, whatever. Now we are not dealing with the units. We are trying to understand how we can resolve the forces. Can you see any angle here? No, there is no angle in this question. But here there is a slope definition, like this part. This is 4. This is 3. That means if you can see this one, that means this point is perpendicular to each other. So what this means, the lateral component is proportional with 4. The vertical component is proportional with 3. So basically, if this is a perpendicular lines, if these are perpendicular lines, you can do this. What is this length? What's the proportional number of 5? Yes, you're right. This part is proportional to 5. So that means this 150 is proportional with 5. So as you can see here, 5 over f over 5 equals fx over 4, fy over 3. So this gives us the the problem. You can calculate from fx and fy easily. If you need, you can calculate the angle. Here, what I try to explain to you, sometimes we give angle, sometimes we give the slope of or proportional numbers, but you get the point how you can use it. It's like an angle. We are not using here direct the sine and cosine. Basically, go back here. What is fx here?
120.
120 over 5. Why I can, yes, 5 times, I can't write. Okay, times 4. Okay, this is 100, for example, 20. You're right. And it's same for the vertical component, fy.
19.
Yes, 5 times 3, right? Here 30 times 3, it's 90. So we can resolve the force according to slopes, given slopes or angle. If we have an angle, we use sine and cosine. If we have these proportional numbers, that's okay, we can use them. Here, yes. Okay, ladies and gentlemen, do you have any questions, comments so far? Otherwise, we are gonna close the session today. Let me see if just a second. There are some questions. Yes, Miraj, it's like 3, 4, 5 triangle. But by the way, during the sessions, I don't take a look to chat. If you have comments, anything else, if you like to say, please do it. Please say to me. I see all these things at the end of the session. So let me take a look, all of you. Okay, ladies and gentlemen, I guess you don't have any question.
Hocam, I was going to ask, we will be using the calculator during the exam, right?
Yes. You're going to use it in the exam because you can't do, otherwise you can't do these calculations. Okay, basic calculations, but it takes time. That's why you have to be familiar with the calculator you're going to use on the exam.
Okay.
Please get a calculator.
I have a calculator I bought for the physics course beforehand. I think it should be compatible. It has function keys for sine, cosine, pi.
Okay, it works for us. It works for us. If it's a scientific, you have sine, cosine, other things. That's okay. You don't have to get a calculator which have the programming functions. We are not gonna use that. You don't have to pay more. Okay. You don't have to pay more. So if you have scientific calculator, that's okay. You have, I think, Dennis. Yeah.
Yes, I.
Any other question, comment, anything else? No, I think. Okay, ladies and gentlemen. Yeah.
So,
yes.
You can access the presentations, right?
I'm gonna share with you. I'm gonna do this presentations in PDF and then share with you. Okay. I guess I'm gonna upload it to the Moodle's page. Moodle page. I think this is a new platform for Bilgi University. Actually, I don't know how to use it. Today, this is the first time I try to use, but I will put this page to the first week's. I don't know. There is a class page, first week's page. I don't know how to do it, but I will do. And then I'm gonna send you an email. Okay, I'm gonna say you, yes, I upload it. Please check. If you have a trouble to get it, then later on we can talk about to solve it. Okay. Okay, ladies and gentlemen, thank you so much. Have a good weekend. Take care of yourself. Okay. Bye bye.
Thank you.
Bye,
Thank you.
teacher.
Thank you.